Hello guys, so welcome to the lectures on the introduction of quantum physics. So today we are just going to be describing the simple concepts of quantum physics. So the first thing which we need to know is that in the universe, everything is made up of atoms, and an atom is just like the smallest unit of an element. And so there are different type of atoms. There are like oxygen atoms, magnesium atoms and stuff. So an atom, it just has a region of space which looks more like our solar system, which is circular like this. And in this region we find some particles which are called electrons. In the region, it is called they call it like an electron shell. And so we find electrons orbiting around electron shells, and this is like an overview of an atom. And so in the inner part we have something what we call the nucleus. So this is our nucleus. And in the nucleus we find two type of particles. Let me just shade the other and leave the other unshaded. So the shaded part we can call it neutrons, and the unshaded part we can call it protons. And so the protons are positively charged and the electrons are negatively charged. And it was a fact that we learned in science long ago, that an electron and a proton, they attract. It is because in the universe the law of charges states that like charges repel and unlike charges attract. So because this is a positive and this is a negative, there is some form of attraction between them, and it is the one which keeps the atoms as they are. It gives the structure of atoms. Because if they are all positive or all negative, then it means that they are going to repel away. We're going to lose the structure of the atom. So this is the introduction to atomic parts, but we aren't more focused on this at this stage. Now what we are focused in was trying to explain that all matter is made up of atoms. And now today we want to deal more with the particle in the nucleus, not in the nucleus, in the atom, which is called the electron. So what is an electron? An electron is like a negatively charged component of an atom, and it is some composition, like it is a fundamental particle. It is a fundamental particle. So with that being said, what we want to focus on is this particle part of this definition. We are saying it's a fundamental particle, and this is according to classical physics, that we say an electron is a fundamental particle. And now there are stubborn scientists in the history who tried to do something in an experiment with electrons. So the thing is, science, quantum physics and stuff, everything about science, it's based on trying to do experiments to prove certain hypotheses, or some experiments can lead to making conclusions about certain things, because it's not necessarily that we have to think of something and do the experiment, but some scientists accidentally discovered some things through experiments. So this is one of it, the discovery of how electrons behave in a double slit experiment. So imagine if we had some electrons which are being fired, E minus, E minus, E minus, they're being fired this way, and here we have let's just put a single slit here, and here we put a double slit, you know, the young double slit experiment, right? So let's see what happens. And here we put our screen. These electrons are going to pass through this, and somehow you are going, as we say the electrons are particles, we are supposed to find some electrons here, E minus, E minus, E minus, and here E minus, E minus, E minus, meaning this region and this region we are supposed to find electrons which would have escaped to go there and to go there. But let's see what happens according to the scientists. This is not what we saw. What we saw was pretty different, and it was interesting. The thing with what we saw is that we saw some electrons here. Many of them, they were found at this part, and we saw other electrons here, and we saw other electrons here, and we saw other electrons here, and we saw other electrons here. And by plotting a graph of intensity against region, we realized that here we had the maximum intensity, and yeah, let's say this is the axis for the graph. Here we had the maximum intensity, and here the intensity was like decreasing, but anyway there was intensity like going onwards, downwards. And here we also had the intensity rising, and here there was also intensity in like this. And what we are seeing here, it is something like a graph. It is a graph which is showing that electrons are not deposited onto only two regions of this screen, but electrons are forming as an interference pattern on the screen. And this is a certain thing which we see with waves only. When we studied waves and we shine light wave onto a double slit, we would realize that we would see this type of interference pattern. But we are seeing this with electrons, but we are saying electrons are particles, and all of us who have studied science or chemistry or stuff, we know that an electron is a particle. But now electrons are acting as waves. So what's happening? Are electrons waves or are electrons particles? We don't know. Let's move next. So a lot of scientists have discovered some interesting things. There is a scientist whom we called James Clerk Maxwell. So Maxwell discovered an interesting thing which led to discovery of many things in the science part. James Clerk Maxwell discovered that for a wire which is current or which is alternating current, would see that it is going to propagate types of fields. This is going to be the electric field, and this is going to be the magnetic field. So magnetic and electric field are alternating on the wire in two axes, and this graph is showing the graph of electric field and magnetic field, and also time or also position, and this is in three-dimensional. So this graph was applied by some scientists, as you said in later video, that Einstein said light was a wave, and the light wave had a region of magnetic field and another region of electric field, and this was showing that light also was a wave. So now we have electron, and now we have light, and we are saying both of these things are acting either as a particle and as a wave. And from this graph we are saying that since light is a wave, it is going to propagate in space as an electric field and as a magnetic field. And this changed our understanding of physics, because scientists had to carry out several experiments to see what happens. So now let me fill this table with light. So when we are saying light is a particle, what's happening? There is a famous experiment in history which was called the photoelectric experiment. And from this photoelectric experiment, we realize that if we take a certain metal and we lay it down, every metal has some positive nucleus at the center and a sea of delocalized electrons moving randomly in the metal, provided that a voltage is not applied between the two regions of the metal. And so if we shine light of a certain frequency onto this metal, the light which we are shining, according to these scientists, we call it photon. It's called a photon. And if we shine a photon onto this metal, we are going to realize that some electrons are going to be knocked out, and these electrons are called photoelectrons. So the thing which is happening is shining a photon releases photoelectrons. So what's happening? We are saying that light is a wave. For now, we don't know that light is a particle, because according to Einstein and some James Clerk Maxwell, we are saying that light propagates in electric and magnetic field, and this is like an electromagnetic wave. And now when light, a photon, is shined onto the metal, if it was a wave, if we shine light of a certain frequency, let's say Fn, like just a new frequency which we are shining onto this metal, we are going to see that if this frequency it doesn't have enough power or intensity to knock out the photoelectrons from this metal, we are not going to observe any photoelectrons being released from this metal. So if it was a wave, by having 2 days shining this, continually shining these photons onto this metal, we're going to have photoelectrons. Why? Because the intensity of this wave, it is the same throughout, but we are shining over a long period of time. So these electrons were going to be absorbing this energy for this long period of time, and then we would realize that some photoelectrons would be released after a longer period of time. But this is not what happens. If we shine the photons onto this metal which have a frequency which is less than the f0 which I'm referring to, it is the minimum frequency required to release electrons from this metal, and it is called threshold frequency. By this shining of this frequency for 5 days a week or stuff without releasing photoelectrons, it is disproving the theory that light is a wave. It means that light is like a certain particle, and one particle which is shining onto this metal, if it has sufficient energy to knock out the electrons, then we have the electrons. Otherwise, no electrons is going to come out. So we are saying light here, it's a particle, and the particle we call it photon. But before we knew that light was a wave, because of from doing that experiment with light and with electrons, we realized that we see an interference pattern. You see now, light is a particle, light is a wave. Also, what's happening here is that we will never ever release photoelectrons from this metal unless we shine light of frequency greater than or equal to the threshold frequency of this metal. So that is the only way which you can release photoelectrons. So now light is both a wave and a particle. Which is which? What should we believe in? Is it truly a wave? Is it truly a particle? Let's go on next. From the what we just discussed about before now, we saw that light is a particle. So imagine if this is a window and this is a window, and these two windows are releasing light. This light is going this way, this light is going this way, you see. Imagine at the point which these two light particles meet. This is like at an angle of theta to this axis, and this is at an angle of theta to this axis. Would realize that according to the laws of momentum, the mass and the velocity of these two particles before the collision is equal to that after the collision. So as a result, I see something like this particle going this angle or at an angle of alpha this direction, and this going at an angle of beta this direction. You see, so as a result, there could be other particles due to momentum which could go this ways, and some going this ways, and some going this ways. You see, so you would see like your light being detected at all these positions. Let me just say photon. Yeah, so this is like where you could find all the photons being detected. But this is not what happens. What happens, you see an interference pattern when we shine light like this, because some light particles are going to superimpose at a certain position, and you could find out that light could be found like as an interference pattern here, instead of being found scattered all around and evenly distributed. This isn't what happens. So this is also going back from that light. At first we said light was a wave, and went on to say it's a particle, and now we are also saying it's a wave. So you see, light is a wave, it is also a particle. So that is how we come to something which is called the wave particle duality. And this proves that light is both a wave and a particle. And watch the next video to see what the wave particle duality says about light being both a particle and a wave. Thank you for watching this video. So you can just like this video, subscribe, and share with your friends. Thank you so much.